So what's going to happen today is they're going to give you a rational function already graphed, and they're going to ask you, yeah, go ahead. Yes, go ahead, Michael. They're going to give you an already graph, and they're going to ask you to come up with what the equation of that rational function should have been. So we have to look for little clues on the graph as to how we could piece all of it together. So I just want to remind you guys that I've kind of been talking about it a lot, this whole multiplicity of the vertical asymptote. If the vertical asymptote had odd multiplicity, it just means that the curves on either side of that VA have to approach opposite infinities. One curve will approach positive infinity, the other curve will then have to approach negative infinity on the other side of that VA. That's when a VA had odd multiplicity. Then we saw in the very first day of section 4.6, when I graphed these two, that when you had y equals 1 over x squared and x couldn't be 0 two times, and you technically had even multiplicity, x can't be 0, x can't be 0, then the VA x equals 0 had multiplicity 2. And we saw that when there was even multiplicity on that VA, then the curves on either side of it, as they approach that asymptote, they have to go to the same infinity. And these are clues that you can use when you go to decide, well, how many factors do I have of this? Would it have an odd multiplicity on this factor? Or would there be an even multiplicity on this factor? So keep that in mind. Same thing with our x-intercepts that bounced. They have to have that even multiplicity to create that bounce. So that's something that you might want to make a squared factor, because we always assume the lowest multiplicity. So we assume 1 for the odd multiplicity, and we assume 2 for the even multiplicities. All right, so when you are constructing a rational functions graph, these are all the things that we use. We find the domain, we identify any VAs, we note the behavior, whether it's odd or even multiplicity, we identify the HA, we note the degree rules, right? We identify the x-intercepts, we note the behavior, does it cross, does it bounce at that x-intercept? We always look for the y-intercept. Technically, the y-intercept, he won't have anything to do when you create the equation, but he's always an extra point that you could use when you have to test something, maybe. He's another known point on the graph. We identify any holes, right? And they would have come from a factor that canceled on top and bottom. And then we can always check for any other known possible points, interception, cross points, and the end behavior of the graph. All right? So guys, when you're going to construct the equation, you want to think of what pieces do you need where? What factor would have been in my numerator? What factor would have been in my denominator? And whatnot. So just to give you a little bit of a cheat sheet, when you are constructing the equation, when you look at the graph, well, first of all, something that you might want to take into consideration is the horizontal asymptote. What rule did you use? Did you use the rule where it was y equals 0 because the bottom degree was bigger? Was it the rule where it was the ratio of the leading coefficients because the degrees were the same? Or was it that slant asymptote, which they don't give you one with a slant asymptote to write, so don't really worry about that. Or was it the slant asymptote that was rule number 3? So something that you want to take into consideration, if it was rule number 2 and it's the ratio of the leading coefficient, then you want to make sure that you put leading coefficients on top and bottom that would create that horizontal asymptote for you. So that's something that you would put in your function when you go to write it. So for example, if it had a horizontal asymptote at -2, you'd want to make sure that you had -2 over 1 when you go to write its function. Or maybe you had -4 over +2, because that would reduce to -2. All right? Something else you might want to look out for when you're writing the equation. The vertical asymptotes are huge. It's one of the first things that we go after. And how do we get a vertical asymptote? We get a vertical asymptote from a factor in the denominator. So you want to make sure that anything that ended up as a vertical asymptote on your graph ends up as a factor in the denominator of the function that you are writing. All right, what else? We go after holes, right? Holes get created when a factor on top and bottom cancels out. So you want to make sure that you put any factors that became holes in your numerator and your denominator when you go to write the function. And then the last thing that you could probably use to create its graph are your x-intercepts, the points where it crosses over the x-axis. How did we get x-intercepts? By setting the function equal to 0 and solving. But in reality, when you do that, it's really just the numerator who ends up getting set equal to 0. So you want to make sure that you have any factors of your x-intercepts in your numerator so that they can create them in that function. Okay? So this is what you'll be looking to do. These are the things that you're going to want to take from the graph and put in your rational equation to create that function. All right? Everything else we can kind of use as just testing stuff. All right, so keep that in mind. Let's try one. Let me move my graph up. Hold on. Michael, were you able to get back? Are you okay? Can I move up?
Yep.
Perfect. So they've asked you to identify certain information, and then we'll use some of that information to create the function. So right now they want to know the domain. So guys, what's the domain of this function? Looking at its graph, you'd be looking for x's that don't exist, right? VA's holes. It has a VA at x equals, I'm going to say that's -1. So clearly -1 is not in this graph's domain. So we would say the domain right now is x cannot be -1. I'm just going to list them, I'm not going to write any fancy notation. All right, I also have a hole right there on the graph, and it looks like it's happening when x is 5. So clearly 5 is not in this function's domain. Okay. Now let's see, they ask for the VAs. Well, I clearly have a VA at the line x equals -1. Now guys, when we do that, let's note what the multiplicity of that VA must have been. If you notice, here's your VA. This curve is shooting off to positive infinity. This curve is shooting off to negative infinity. So since they're approaching opposite infinities on either side of this VA, that VA must have had odd multiplicity. So it must have only been that odd number of factors for that x equals -1. So I'm just going to put a note, odd multiplicity. All right, I don't have any other VAs. The horizontal asymptote is clearly right here with a line y equals 2. So normally when you end up with a horizontal asymptote at y equals 2, it's because you used the ratio of the leading coefficients. Otherwise, it would have been y equals 0 if the degrees were the same, or it would have been a slant asymptote if the top degree was bigger. So the fact that we have this HA at a number tells me that the degrees must have been the same. All right, x-intercepts. It looks like I only have one x-intercept, and it's right there at x equals 2. Note the way it crosses. It's a pure cross, so he must have had odd multiplicity. He didn't have even multiplicity that made it bounce. He must have had odd. The 5, because the hole. A hole would create a number that's not in the function's domain. So the hole happened when x is 5, so 5 must not be in this function's domain. Does that make sense, Michael?
Yes, thank you.
Perfect. All right, so now the x-intercept is just x equals 2. And again, I'm going to note that he must have had odd multiplicity because it crossed over. Even multiplicity would have bounced. All right, the y-intercept, again, not something that we may use to create the function, but we could use it as a test point later. It's another point that we know that is definitely on this graph for sure. It looks like it's right there at 0, -4. And then the holes. Some have them, some don't. This one had it. All I really need to know is the hole happened when x equals 5. So whether you put x equals 5 or whether you try to put an ordered pair, it kind of looks like it's the 0.51, but holes sometimes are pretty ugly. So for all I know, that's the 0.5 and 0.88. But all we really need is to know that the hole happened when x is 5 in order to construct his function. Okay, now let's use this information to write his equation. So we're going to start with f of x equals. Normally when I have you write an equation, I start you with that a value, that leading coefficient. I'm not going to do that because we're going to start with our leading coefficient right away. So guys, it's a rational function, so we need a top and a bottom. I know I had an HA at the line y equals 2. So I must have needed coefficients that reduced to 2 over 1. So you can easily put 2 over 1, or if somebody wants to live on the edge and put 4 over 2 or 12 over 3, go ahead. I'm sorry, 12 over 6, that's fine because that'll reduce to 2. But if they make you multiply it out, yours is going to be harder to multiply out than ours is just by using 2 over 1. All right, thumbs up. Everybody understands why I put the 2 over 1 there? Everybody's good? Okay, now I go to my VA. If I had a VA at -1, then I must have had a factor of x plus 1 in my denominator that told me that's going to be a VA. So I definitely need a factor of x plus 1. And since you had that odd multiplicity here, they're going to opposite infinities, I know it's just a factor of 1. It doesn't have to be squared or anything like that. All right, then I also have, I have wholes. Guys, I had a whole when x was 5. So that means I must have had a factor of x minus 5 and x minus 5 on top and bottom, because they would have canceled to create that whole. Because remember, your whole comes from a factor that canceled on top and bottom. And then the last thing that I could really put into this function is the fact that I have x-intercepts that would have been factors in my numerator. So guys, I had an x-intercept at x equals 2, and it was a cross, so it's odd multiplicity. So I must have needed a factor of x minus 2 to create that x-intercept and make it cross. All right, guys, you've used everything you could possibly use to create this function. Now all I would do is make sure, does it fit the HA rule? If I'm going to have an HA at y equals 2, do I have a same degree over a same degree? Guys, if I multiplied this out, it would leave with a 2x squared over a 1x squared. So that would definitely have that same degree on top and bottom and create that horizontal asymptote at the line y equals 2 over 1. And you're good to go. I don't think they ask you to multiply it out. I think you're allowed to leave it in factored form, so you should be fine. Is everybody okay? Yes? Any questions on that? All right, try another one. I'm just making sure the order is the same. The next one. Yeah, this is the notes I posted. Okay, we're good. All right, let's look at this one. Let's identify the information they have asked us first, and then we can use it to kind of build our function. The domain. Well, who are the bad guys? Guys, they actually named your VAs for you here, which is awesome. That's less work for us. So clearly, x can't be negative 5, and x can't be 2, because those are VAs. I don't see any holes on any of these graphs, or any of these curves, so it must just be our VAs are the bad guys. So x can't be negative 5, and x can't be 2. But time out. You see how when x is negative 5, they approach opposite infinities as they approach this VA. So that means x equals negative 5 had odd multiplicity. But you see x equals 2? See how they approach the same infinity on this side of the graph? That must mean he had even multiplicity. That must have been a repeated factor to create that VA. All right, so take note of that. All right, so our domain is x cannot be negative 5 or 2. Our VAs are x equals negative 5, and he must have had odd multiplicity. I'm just making a note of that. And x equals 2 must have had even multiplicity. All right? The HA again, it looks like it's the line y equals 2. So normally when you end up with an HA like that, it's because the degrees were the same, and you ended up taking the ratio of those leading coefficients. So we want to make sure that in the end, the top and the bottom degree from our factors are the same. All right, x-intercepts. I have none over here. It looks like I have an x-intercept at negative 2, but guys, look how it touches. It bounces. So that must be an x-intercept that had even multiplicity. So I'm going to say x equals negative 2, but it had even multiplicity because it bounced. I have another x-intercept, it looks like, when x is 5, but it's just a cross. So we're good. That's odd multiplicity. That's normal. All right, the y-intercept, it looks like it's right there. It's the 0.02. But like I said, we don't always need to know the y-intercept. Sometimes we'll need it as an extra test point, but that's only in certain cases. Oh, negative 2. Good job, Case. Good job. Good job. Just kidding. All right, and then the holes. I don't see any holes. So, like I said, that's less factors that we're going to have to create on top and bottom that cancel to make that hole. So there are no holes. All right, let's do it. Let's create this graph. I try to start with leading coefficients that I need. So if I'm going to have that y equals 2, I'm going to need leading coefficients that reduce to 2. So I'm going to put 2 over 1. Again, you don't need the 1 on bottom. I just have a habit of putting it there. All right, VAs, right? VAs come from factors in your denominator that did not cancel. So I would need a x equals or -5. I would need a factor of x plus 5 to create this VA. And like I said, I would only need one factor because they go to opposite. He had odd multiplicity. So I would definitely need one factor of x plus 5. And then I definitely have a VA at x equals 2, but it had even multiplicity. So I would need this one to be a squared factor, or x minus 2 squared. All right. And then I don't have any holes, so there's no factors that I have to write on top and bottom that cancel. And then the only other thing I would need in my numerator are any factors that create my x-intercept. All right, so I had an x-intercept, we said, at -2 with even multiplicity. So I must need an x plus 2 squared. And then I had an x-intercept at 5 with odd multiplicity. So I must need a factor of x minus 5 to create that. And then everything that's usable to create this function is taken care of now. Now I would just double check. If I had that HA at 2, I would need the degree of the top and bottom to be the same. So guys, if I multiplied all this out, he would leave with an x squared after I FOILed it. So 2 times x squared times x would be 2x to the third over 1 times x, and this would be an x squared. Once you FOILed it all out, that would be a 1x to the third, right? X squared times x is x to the third. So I do end up with a degree 3 over a degree 3 with leading coefficients that reduce to 2. All right, everybody okay? Everybody good? All right, I want to do one more because I want to show you, like, sometimes it doesn't work out that perfect every time, and there's one extra step you have to go to create some factor that you can't actually see from any of this information. So this is the example I ended up adding. This was the third example. I put this one here because I'm going to stop. After I do this one, I'll let you guys do this one on your own, and I'll fill this one in on the filled in notes. But I want to show you this one. All right, here we go. Ready? All right, so the domain. I'm looking for holes. I'm looking for VAs, numbers that can't be plugged into this function, the bad guys, right? Clearly, I have a VA at x equals -1. And note, guys, look at his behavior. They're going to the same infinity. So he must have had even multiplicity, right? X is equal to 2. So x must not be allowed to be 2 because he created a VA. And look at him. He has the same infinities on either side. He must have been even multiplicity, right? I don't see any holes. So the only bad guys are -1 and 2. All right, we got a VA at x equals -1. They already named it for us. And he must have even multiplicity the way these graphs are going off to the same infinity on either side of him. I have a VA at x equals 2. Again, must have that even multiplicity to go to the same infinity on either side. All right, my HA. I have a horizontal asymptote at the line y equals 1. So again, I must have had that same degree, the ratio of the leading coefficients to create that, right? The only other case would be they give you is if the horizontal asymptote was the line y equals 0. And then all you have to do is make sure the bottom degree is bigger than the top degree to create that one. All right, so y equals 1. All right, I have x-intercepts. I have an x-intercept at 1 and it crosses, so we can assume odd multiplicity. I have an x-intercept at 3, so I can assume, and it crosses, I can assume odd multiplicity. I have a y-intercept. Actually, it's a cross point on your HA, which again doesn't matter if it crosses, it's fine. But I have a y-intercept at 0, 1. And we did not have any holes, so that's a no. All right, let's see if we can create this guy. All right, so I like to do my coefficients first if I need them. I know I have to have a leading coefficient that reduces to 1 in order to create this HA. So again, the easiest thing to do is let it be 1 over 1. But you could do 2 over 2, or 3 over 3, or 4 over 4. But if you have to multiply this out, 1's our guy, because if I put 1 over 1, I can actually erase them in a couple seconds when I don't have anything, I don't need anything in front of these factors. But I like to put it just to know that I've made it part of my process. All right, now let's go to VAs. I had to have a VA at -1, so that must have been a factor of x plus 1 that got me that. But remember, I need even multiplicity. All right, I have another VA at x equals 2 that must need that even multiplicity. So I must have had a factor of x minus 2 quantity squared to create that vertical asymptote. All right, the next thing I would normally do is put my factors for my hole, anything on top and bottom that I would need to cancel, but I didn't have any holes, so I don't need that. All right, now I'm looking to put my x-intercepts as factors in my numerator. So I had an x-intercept at 1, which means I must have had a factor of x minus 1, and he must have odd multiplicity because he crossed. I had a x-intercept at 3, so I must have had a factor of x minus 3, and it must be odd multiplicity because it crossed. Okay, so we think like, oh, that wasn't too bad, we're good to go, right? But remember, in order to create that HA at the line y equals 1, I must have been following asymptote rule number 2, where the degree on the top and the bottom were the same. Guys, if we multiplied this out, I would have a 1x squared over an x squared and an x squared on 1x to the 4th. So technically, if this were the equation that we wrote, we should have had a HA at y equals 0 because the bottom degree was bigger. So we don't have it. We're not finished yet. We didn't do anything wrong. We're just missing something. The only thing that could fix this is, guys, I'm missing a degree 2 factor on top, right? I'm missing a quadratic factor. So an x squared and an x squared would become x to the 4th. I'm missing some quadratic factor on top. And the only thing that wouldn't change any of this information is it must be a factor that created complex zeros. I must have had factors in my numerator that when I set them equal to 0 and solve for like x-intercepts, they must have been imaginary numbers. So we are missing some quadratic factor that had imaginary roots in our numerator. So I am missing some quadratic factor that when I set it equal to 0 and solve, I get imaginary zeros, right? So fill in the fact that you need x squared plus c. There's some quadratic polynomial that is missing that's going to make it a degree 4 over a degree 4. So now what you're going to do, I can't remember, our book either uses C or A, if you were to look up the way they did it. I'm just going to use C. What you're going to do now is now you're going to borrow the y-intercept, and you're going to plug 0 and 1 in for x and y, and you're going to solve for what you need that number to be in that factor. All right, so we're going to plug it in. Plug 1 in for y, and plug 0 in for all of those factors. So 0 minus 1 is -1. 0 minus 3 is -3. 0 squared plus c is c. Over 1 times 0 plus 1 squared is 1. 0 minus 2 is -2 squared is 4. So we're going to end up with 1 has to equal 3c over 4. Now you got to solve for c. What's that missing number that's going to create that missing factor there? I'm just going to times by the reciprocal. And c is 4/3. So you are missing a factor of x squared plus 4/3 in order to create a polynomial function where the degree on top and bottom would be the same. So all you have to do is pop 4/3 in there and call it a day. And there you have it. Okay? So just be careful, because sometimes, majority of the time, they probably work out very nicely, but every now and again, you'll get a case like this, okay? And then the only thing I can warn you, I don't think they assigned it, which is why I didn't put it. If the HA was y equals 0, again, that just means that you just have to make sure that the bottom degree was bigger than the top degree. But every now and again, if you notice that your graph, like maybe this curve approached the asymptote from below, but your equation, when you test it, it approaches it from above. Sometimes you have to just throw a negative sign in front of the function that you wrote if it's that whole bottom degree has to be bigger. But like I said, I don't think they assigned one like that in the homework, so I just didn't even bother putting an example like that. All right, I'll leave this one for you guys if you want to try it. Guys, just be careful because the picture is horrible. Here is Y, so this is your Y-axis, and here's X, so this is your X-axis. Otherwise, it's like really, really, really hard to read the graph and see what numbers you're at. But I'll fill it in on the filled in notes in case anybody wants to check, okay? All right, guys, does anybody have any questions for me? Are you guys okay? Okay, well then this section is done. We have seen everything. The majority of it is just creating the graphs, but there's just a couple where they could ask you to create the function given the graph. All right, I created one homework for this assignment. It's only 4 questions. And then that I didn't make due till Sunday night. So from here on out, tomorrow included, you are working on homework or you are working on that study plan. Our quiz will be Monday. All right, let me just double check the attendance and I'll let you guys get out of here if you don't have any questions for me.